All right, so this is lecture 11 for distributed energy resources. Sorry, no, lecture number 12. Today we're going to be talking about basically looking back at the modeling unit of the class, which we've done for the last 8 or 9 lectures, and just kind of refreshing our memories about the things that we learned about, and then coming up with kind of a unifying modeling framework that we could use to capture most of the DERs that we considered. So there's kind of battery type models that we can put all the different devices into with different parameter definitions and things like that. A reminder that Thursday's class will be on Zoom only, so no in-person class on Thursday. Um, and it won't be a structured class, so you can just bring your questions about stuff that we have talked about so far in the semester or whatever else you want to discuss, and we'll take that hour and 15 minutes there to basically just go through those. So the TA and I will help answer questions. You can do, peer answering of questions and things like that. But the idea is that this is the last class before our midterm exam, which we will post, I think, around noon Eastern on Sunday, this coming Sunday. And then it will be due 24 hours later on Monday. So then on Tuesday of next week, we will start basically the second unit of this class, which is about decision making, essentially. So we know how to model a variety of DERs at this point, but we don't really know kind of how to do stuff with those models. So what if we want to figure out how big of a battery to put in, or how big of a solar array to put in, or how to operate an EV charger, or how to operate a thermal energy storage system? So we'll learn about numerical or computational optimization methods, ways that we can basically use computers to inform those decision-making processes. Yes.
For the exam, will it be on Brightspace or the website?
Will the exam be posted on Brightspace or the website? How about Brightspace? Sound okay? And then I think you guys will get like an alert from Brightspace when it goes up, maybe. Anyway, I'll send an email. We'll post it on Brightspace and I'll send an email. So keep an eye on your email on Sunday, but we'll aim for noon on Sunday. So you guys get Sunday afternoon and then you get some of Monday morning as well, if that works better for your schedule. Yes. Yeah, so the exam is completely individual. On homeworks, you're welcome to work with other people. On exams, no. We haven't, this is the first time. So last semester I didn't give an exam. And so, half the class roughly is in the online section. So if everybody was in person, I think we'd just do like probably written exam during one of the class periods. With online students, we can't really do that. I don't want to mess around with trying to proctor on Zoom or something like that. I think we all did enough of that in the peak kind of COVID era that we might not want to go back to that. Yeah, so it'll be take home, it'll be individual, and we haven't yet decided what the ground rules are in terms of what resources you can use. So certainly you can use lecture slides, lecture videos, your own homework solutions, any of your own notes. Like, of course, those are all fair game, but beyond and not other people, right? But there's kind of a spectrum of stuff in between there that maybe you can use and maybe you can't. So my current thinking is that we will ask you basically to use only the course materials and your own notes and solutions. But of course, there's basically no way that we can police that. So it will more or less be on your honor. Does that sound fair to you guys? Okay. Yes.
Do you know what, again, I'm sure you might talk about this, but like in general, what it might consist of? Because if it's on Brightspace, like, will there be like a quiz where it's like multiple choice questions, or is it mostly going to be about coding, or what exactly?
So the question is like roughly what will the exam format be? And no, there won't be like a multiple choice like thing on Brightspace that you have to fill out. It'll just be a PDF like the homework assignments.
Okay.
You'll take it and you'll create your own solution, either typed up or written out on a tablet. You can do it on paper, take photos, whatever you prefer. So basically just like doing a homework. There probably, I haven't totally finalized everything yet, but it'll be probably 3 or 4 questions. And a couple of the questions might have computational parts, but it probably won't be like, here's a whole bunch of starter code, fill in the appropriate details. It won't be like the homework coding.
Okay.
It'll just be like, write 10 or 20 lines of code in MATLAB or Python. Okay. Other logistical questions? All right. And we can discuss more about the format and stuff like that on Thursday as well. Okay, so that brings us to today's lecture, which is basically, again, a wrap up of the modeling unit of the class. So basically, we'll think through how we can view almost everything that we've learned about as a sort of a battery or a thermal battery or something like that. Solar photovoltaics won't really fall into this modeling framework, but I think everything else that we talked about will. So stationary batteries, electric vehicle batteries, passive thermal energy storage from basically the air and the thermal mass of buildings, active thermal energy storage from things like water heaters, ice storage systems, and so forth. I think that's about it. Yep. So we'll talk about those. And then this kind of one model to rule them all. So this is basically spelling out a sort of modeling framework that is general enough to encapsulate everything that we've talked about in the above sections here, but not so general that we go beyond that. And then we'll talk about a variety of DERs that are, I think, important, but that we haven't really spent much time on so far. So that'll include things like appliances, where you can schedule their operation, wind turbines, fuel cells, generators, and things like that. Okay, so we're just going to go through as a little bit of a review, and then again, this kind of generalization practice. We're going to go through the most of the DERs that we've talked about. So we'll begin with the first one that we talked about in lecture number 3, which is a battery. So the state of a battery model. There are many ways to approach all of these models. So you can do transformations, and rather than thinking about energy, you can think about charge that's stored or something like that. But I think these are fairly general and intuitive modeling approaches. So at least in this approach to modeling a battery, we think of the state as the stored chemical energy, the chemical potential energy. The action, the thing that we can determine, the knob that we can twiddle, we think of as being the chemical charging power that we're putting into storage or taking out if we're discharging. And then there's an output, which is the electrical charging power, or if it's negative, the discharging power. And this is what we exchange with the power grid. We also have some parameters. So we have the energy capacities. Always we will have an upper energy limit, and sometimes we might have a non-zero lower limit on the stored energy. So for example, for a backup battery in a house, you might be able to play with, say, the upper 60% of its capacity, but the homeowner might say, never let my battery drop below 40%, so that I always have, some buffer to run critical loads on a power outage, something like that. And then we have chemical power capacities related, I guess, as well to the electrical power capacities here. So this determines how quickly we can discharge and charge. We also have the time constant, or the self-dissipation time constant of the battery. And we talked about how this might be in the order of 1,000 or more hours. And this governs basically the depletion of charge when a battery is just left unplugged. And then we have a dynamics parameter A and B. And A here basically is just our exponential of the time step divided by the time constant. And B, we found from the kind of problems that I drilled into you guys many times over about writing down the solution to these linear differential equations. So the discrete time dynamics, I'm skipping directly to the discrete time form rather than going from the continuous time form. We get that the new stored energy xk plus 1 is equal to A times the old energy plus B times whatever the action was that we took at that last time step. We have our state, our energy constraints, also our power, our action constraints. And then there's an equation that relates the output here, which we think of as the electrical power that we exchange with the grid, to the input, which is the chemical, or the action, I guess, which is the chemical charging power. And so here, the electric power, in this case, let's see, U is positive. This means we are charging the battery. So if we had a perfectly efficient battery, an efficiency of 1, we would lie right along this line, y equals x, or p equals u. But our battery is not perfectly efficient, so we use somewhat more electrical power in order to deliver that unit of charging power. And then conversely, when we're down here, now we're in the discharging regime. If we had a perfectly efficient battery to do 1 unit of discharging chemical energy, we would get back 1 unit of electrical power. But actually, our battery is not quite that efficient, so we get back somewhat less. And so we get this kind of, I don't know what you call this shape, but angled thing here. Questions about this? Okay. So an electric vehicle, basically, we again model basically as just a battery with wheels, a battery that's unplugged sometimes when people are out driving it around. Um, so we basically have the same modeling definitions, but now our chemical power capacities, the action constraints over here, the U min and U max, become time varying. And the time variation comes in from basically the state of whether the vehicle is charged in, or sorry, plugged in or unplugged during a time step. So if we are plugged in, then the constraints look pretty similar to what we get from the stationary battery model. If we are unplugged, basically you can't charge and you can't do a discharge from the vehicle to the grid. You can, of course, do a discharge for driving. And then most electric vehicles do not have what's called bidirectional charging, meaning they can only absorb energy. They can't give energy back to the house or to the grid. And so for most EVs, this maximum discharge power is actually zero. All right, and then into our model, the sort of discrete time dynamical system model, we add a disturbance term here, which is related to the energy that's dissipated for driving. So here, D is the distance that we drive. Alpha, we call the energy intensity of driving, so kilowatt hours per kilometer. And then delta T is just the duration of the time step. So if you multiply these out, we have, let's see, kilowatt hour per kilometer. D would be in kilometers. So we'd have kilowatt hour in the numerator, and then we divide by the time step to get basically the average power in kW that's used over the time step for driving. So that lands us in our final model here. It looks a lot like the stationary battery model, but now we have this W term as well. Yes.
So that W term was the energy being spent to drive?
Yes. Yeah, W is the power, sorry, the chemical power that is dissipated from the battery in order to drive the vehicle around. Yeah. Mm-hmm. And then the action constraints look similar, but now they are potentially time varying. And again, the time variation here just encodes basically whether the vehicle is plugged in or not. Okay, so that covered, I guess, our first lecture, our first sort of lecture in this unit of modeling after we did the introductory material. Then we spent a couple of lectures talking about buildings, and in particular talking about how buildings can be viewed as kind of like a battery if you squint, sort of like a thermal battery. And so we'll talk again through basically how that stuff works. And I learned last time that this was a little bit confusing and that I should start with a picture. So I'm going to do that picture first and then backtrack a little bit to go through some of the math. But so here I'm showing the electric power that's used, say for, I don't know, maybe this is a hot day, maybe used for air conditioning. And so the dashed orange line here is the baseline power consumption. So this is if you just kind of let the building do what it would normally do without any interference. This is how much electricity would be used for air conditioning and everything else in the building. So this might be late afternoon, around 4 p.m., air conditioning load might peak. And then P, here the thing in blue, we might call the adjusted or the perturbed power consumption. So the idea is that we come in here and we do something different to the building. We knock it away from this baseline, the dashed curve here. So let me ask you guys, so what is happening during this period here where the blue is above the yellow? Yes.
Like power energy is being added to the system. So I guess if it were thermal mass, like hot people are coming in, warm people are coming into a building, or something is happening. It's hot outside or something.
So it's hotter outside. Hot people are coming into the building, something like this. And that's causing basically more energy usage. Okay, Jennifer?
Oh,
You're trying to, instead of like using the peak energy during like 4 p.m. on peak load, to kind of shift the load a little earlier.
Right.
Preheat the building a little bit harder than they would when they have a lower demand. That way they can like ride on that, thermal capacitance throughout like the peak.
Yeah, so I would say that those are both right answers. The one that I had in mind is the second answer, that this would be like a deliberately controlled thing. So again, if this is air conditioning, this is about 4 p.m. The overall grid might be like panicking if this is a super hot day. They might be running out of capacity, it might be at risk of power outage, something like that. So in order to alleviate strain on the grid, we want to basically shed some load during that period, reduce our power consumption. But if we just do that without doing anything preemptive, then basically we just let the building get really hot, and so people might get kind of annoyed. So this is what you might call a load shifting profile. So the idea that I had when making this was that we'd be pre-cooling the building, say from, I don't know, 2 p.m. to or noon to 2 p.m., something like that. And then, bringing the temperature down, not super cold, but to colder than normal. And then during the kind of late afternoon when it really gets hot, we use some of that stored cooling from the capacity of the building in order to reduce the power consumption. And then there might be a recovery period after. So we might actually let the building get hotter than usual, and we might need more power to bring it back down to its kind of normal state. But Oscar, to your point, that would be like somebody somewhere is deliberately twiddling knobs in order to knock the building away from its like baseline behavior. You also could have weird, unexpected stuff happening in the building that would knock it away from its baseline behavior. So for example, people could open up a bunch of windows and let in a bunch of hot, humid outdoor air. People could have a dance party with all their friends or whatever and cause more internal heat generation, stuff like that. So that's a fair point as well. Yes, Zach.
Looking forward to the optimization parts of the class, we would determine if that's actually an efficient thing to do or not.
Yeah, so as we move, thank you. That's a great segue to the lectures that'll come up next week. But as we move into the optimization phase of the class, we will learn about how to use computer tools to basically design profiles like this. So if you say, look, the price of electricity is going to get crazy high in the late afternoon, maybe it steps up from a low price to a high price around here. You might ask a computer, give it a model of your system and say, what is the best way to operate it? And it might give you back a profile that looks like this, that says pre-cool and then drift and then re-cool, I guess. Okay, so that is the illustration. Now let me go back to all the annoying math. So here, if we view the indoor air of the building as kind of like a thermal battery, we could define the stored thermal energy, whether it be for heating or cooling. I guess here I'm thinking mainly of a heating scenario, but all this stuff works with a sign change for cooling as well. So basically that's the thermal capacitance of the indoor air and whatever shallow thermal mass is tightly coupled to it, times the temperature deviation. So here T would be the actual temperature that would correspond to the blue curve in the graph that I showed. And then T hat would be basically the baseline temperature. So this would correspond to that dashed line, the orange line that I showed. And then similarly, the action here would be the deviation, the perturbation of the actual thermal power that we put into the building minus its baseline. And then the output here that we care about is really the electric power perturbation, which is, or maybe the electric power we could call the charging power that we're putting into either charging or getting back by discharging the thermal mass. And that would be QC divided by the COP eta here. I guess that's right. There's other ways you could view this, but I think that's fine. Okay, and then we define energy capacities related to basically how much you can perturb the temperature away from the baseline. So Tmin might be the minimum acceptable, kind of comfortable temperature for people. So during that pre-cooling phase, you might say, look, how cold can we make the building before we start annoying people? And then Tmax would be how hot can we let it drift, again, before we annoy people. And then we have thermal power capacities related basically to the capacities Qmin and Qmax of the heating or the cooling system. We again have a self-dissipation time constant, but for the thermal mass of a building, this time constant for, say, a house, R might be on the order of 2 to 3, C might be on the order of 2 to 3. So this thing might be about 6, something like that, hours, compared to 1,000 hours or 1,500 hours that we might have for electrochemical energy storage. So it's a lossier battery in that sense. And then we have our dynamics parameters that feed into our dynamics equation, and those look basically the same as they did for the electrochemical battery. We have state constraints that are in general time varying, and the reason for that time variation comes in from the fact that these Tmin and Tmax, the kind of lower and upper allowable temperatures, could vary with time. For example, they could vary with occupancy of the building. If nobody's in the building or very few people are in the building, you might have relatively loose kind of bounds, allow a lot of temperature deviation. But if your building is fully occupied, you might have tighter constraints. Yes.
So the QC min, QC max, that's based on like what the material.
So the QC here and the okay, so QC would be the thermal power that's delivered to the space. So for this room, that'd be like what's coming off of the radiators. And then the min and the max of that basically are like how much heat you can get out of that, heat exchanger area, how hot the working fluid is, stuff like that. Yes.
Value there.
And the nominal value Q hat, again, is sort of like if you kept the building exactly at the profile T hat, then you would use Q hat thermal power.
I guess earlier you defined U like max and min as being like the balance that we can actually produce power at. But if it's just defined as the difference here, should we actually take QC max and min? Like find the total power that we can charge at, like or dumping it in, it's like min and max actions that we can do, yes, but that's not quite equal to the total power.
Yeah, so here U really is it's like a power adjustment or a power perturbation. It's like you can think of it roughly as like the size of these wiggles that we're allowed to do, the deviations of the blue from the orange here. So if you want the absolute value relative rather than a perturbation, if you want sort of the height of the blue curve, then yeah, that would not be U. That would be like you'd add in the nominal to U or something like that. So if you wanted QC, the actual amount of heat that's delivered to the space, you would take the heat perturbation, then you would add it to the baseline Q hat. And that would give like the actual KW that's coming off of the radiators in the back of the room. Does that make sense? Ish?
On slide 3, we talked to like we define it as the difference there as the power over eta. But then you, I guess on slide 5 or 5, then you say that that's the QC over eta. I guess that's one reading here.
Oh, yeah, sorry, the output here, P, this is weird actually. So there are various ways that we could think of the sort of electrical power. And here I'm thinking of P as being like, yes, not the perturbation. So this is P here would be like if this whole thing is 100 kW from a big commercial building, P here would be 110 or something like that. Whereas the deviation might only be 20 kW.
In the EV example, that P is the power is equal to the perturbation, so that's why that holds.
Right. There's no sort of nominal scenario for the battery. Now you could look back at this battery model and you could say, look, on a normal day, we charge overnight, California, say, on a normal day, there's tons of solar, from 10 a.m. to 4 p.m. So our normal pattern is we charge like a bandit during those periods, and then we discharge in the late afternoon. When solar power is ramping down and gas power is ramping up and stuff like that. So you could say that's our nominal day. You could put hats on that profile. And then you could say, but we can wiggle and deviate a little bit from that profile if we want to. So if something unexpected happens, there's a bunch of clouds, unexpectedly cloudy, then we're not able to do that sort of full charge during the day profile. So you might deviate from that somewhat.
Wow.
Right. And so you could write down a perturbation model for the stationary battery as well. And then there would be like a P, an output term that would be defined as a perturbation rather than a magnitude. That's a good question. And honestly, this is the way that I formulated this is slightly confusing now that I went through it. But yeah, you could equally well put a QC minus Q hat in the numerator here, and then you would define P not as the absolute power, but as the deviation, the perturbation. Okay, so that's the air. We also talked about how you can store, I guess I didn't go through these, but so we've got a dynamics equation, we've got our constraints, and then we've got this output equation. again, multiple ways that you can kind of skin this cat, right? So you can think through ways that you could come up with models that are more useful for different applications, and they might look somewhat different for this. Okay, so we can play a similar game with the deep thermal mass. So this again would be like the cinder blocks, the concrete that's in the walls, in the floor, and things like that. So basically, we charge that by warming up the indoor air or cooling down the indoor air if we want to store sort of cooling. And this again is defined in a sort of perturbation sense. So again, to get the energy capacity, we take the thermal mass and multiply it by the temperature deviation. Our action here is the temperature deviation divided by the resistance between the indoor air and the thermal mass. And then our output equation, again, we can think of, I guess here I'm defining it again as a magnitude, not as a perturbation, but we could play with that definition if we wanted to. But this is the electrical power, basically, that either we put in for charging or that we get back from discharging. And then we've got capacities. These are defined exactly the same as the air, for the energy capacities. The thermal power capacities are defined a little bit different. So basically, the limiting factor in our ability to dump heat into the deeper thermal mass of a building is really how hot or cold we can make the air around it. So basically, we don't have, at least for most buildings, at least in the US, we don't have a way to directly heat or cool the thermal mass. In European buildings, it's more common to have something like a radiant floor system, where you'd have a big concrete floor with a heat exchanger in it, and so you could directly heat up or cool down the thermal mass. But basically, for most purposes, at least here in the US, you would warm or cool the thermal mass by first warming or cooling the air and then letting the heat bleed into the thermal mass. So you take the delta T, divide by R, and that gives us basically our action constraints. We have a time constant again, and the dynamics parameters are defined basically in the same way. And so the model that we get is essentially the same as the indoor temperature thermal battery model, but now we have this weirder looking output equation. And I will show where this output equation comes from in just a second. So this is going back again, like at this point, 3 weeks or something like that. But if we had a 2R, so 2 thermal resistors and 2 thermal capacitors model, and if we assume that the air temperature is approximately in steady state. So this means basically it might change, but it'll undergo step changes that are very short compared to the timescales that we think about when we're charging and discharging thermal mass. Okay, so in that case, you could go back to the 2R2C model, look at the equation that governs the indoor air temperature, and set the time derivative of the temperature equal to 0. And then you would get this equation here by solving for QC. So in the baseline scenario, again, that sort of orange dashed line, we would get basically the same thing, but now we would have hats on all the sort of baseline values of these parameters. And then if we take the difference, so subtract equation 2 from the top equation, call it 1, we get our expression for the thermal power perturbation. And this is fairly straightforward algebra to get to here. And then we just recognize that this thing is equal to U times the thermal mass. That just comes from the definition of this perturbation U. And that this thing over here is the stored energy divided by the thermal capacitance C. So we write all that down, and we remember this thing here is the time constant. And then taking Rm and multiplying it through here, we get this term, pre-multiplying the action there. And that is the equation that showed up on the previous. All right, so that's passive thermal storage, basically taking advantage of the fact that there is energy storage capacity in the air, the thermal mass of buildings. But what if we want, something more, I guess, intentional than that? We talked about various ways that we could model and implement more active thermal energy storage systems. So we talked about sensible, meaning we change the temperature. And we talked about a lumped sensible model, meaning we assume that the temperature everywhere in the storage tank is the same. We also talked about a stratified sensible thermal storage model, where there would be a hot layer of fluid sitting on top of a cold layer with kind of a thermocline in between. So we'll go through those. And we also talked about phase change thermal storage. And so we'll talk about that one as well. Okay, so here, again, slightly confusing, but we introduced these what we call a datum for the thermal energy. So a baseline temperature at which we say that the energy is defined to be 0. So here the energy storage is defined as C, the capacitance of the storage medium, times its actual temperature minus the baseline temperature there. And then our action here is just the thermal charging power, and the output is just the electrical power. Capacities are very straightforward. In fact, these look just like the passive thermal mass. And then we have thermal power capacities related to basically however we charge or discharge a thermal energy storage. So these could be related to heat exchanger sizes. They could be related to pumping capacities and things like that. We have a time constant, again, is just RC. Although typically the R and the C will be significantly larger for an active thermal energy storage system than they would be for a building. And yeah, and then we get the parameters and the disturbances that follow these definitions here. So here QD is basically the rate of heat withdrawals from the tank, for example, to heat a building. And then TA, this is the ambient temperature sort of surrounding the thermal storage device. So those things all form into a dynamics equation that looks exactly like it did for electric vehicles, just with different sort of notions of what each of the terms that show up in this equation mean, how to interpret them. We have time varying state and action constraints potentially. And our output equation basically is just taking the thermal power and dividing it by the COP in order to get the electrical power. Okay, so that was for the lumped sensible model. We also have the stratified sensible model where we deliberately sort of avoid mixing inside of the tank. And I guess in the interest of time, I'm going to kind of rip through this slide, but you can go back to the thermal storage lecture and remember the definitions of all of these things. But basically, Y here is normalized between 0 and 1, and it pretty much tells us the height of the thermocline, and it's measured from the top of the tank, so that when Y is equal to 0, the thing is fully charged, and when Y is equal to 1, the thing is, oh, sorry, opposite. When Y is equal to 0, we say that there is no stored thermal energy, and when Y is 1, we say that there is it's full. Okay, and then capacities here look basically the same as they did for the previous case. And here TH and TC, these are the temperatures of the hot column of water and or whatever the storage medium is, and the cold column. And then this TSS is again just a sort of generic temperature at which we define the stored energy to be equal to 0. So this could be the cold layer temperature, or it could be the ambient temperature, something like that. Okay, and then we get parameters and a disturbance that look very similar to what they did in the previous example. So the overall model looks just the same as it did for the lumped sensible case. But actually, in this case, the energy capacities are not time varying. They're just constant. And then the latent thermal model here. So again, we can choose basically a benchmark temperature at which we define the energy stored in the tank to be 0. So you can think of the energy stored in a latent thermal energy system as the energy that's required to bring, say, the temperature from this benchmark TL, maybe the ambient temperature, up to TM, which is the melting point of the phase change material that we're using to store energy. And then L, this is the latent heat of fusion, and ML is the mass of fluid or material in the tank that is melted. So if nothing is melted, and if TL we choose to be equal to the melting point, then we'd say we have 0 energy in the tank. Okay, thermal capacities. So here, basically capital M is the total mass of material that we are storing. So when little ml is equal to capital M, we get that the tank is fully charged. And when m sub L is equal to 0, none of the mass is melted, then we define that as kind of the minimum charge level. And then everything else more or less looks the same as the other thermal storage models. Yes.
When we're doing B of U plus W, how does that look given? I forget. Maybe not on this one, but like on the last type, we have B is equal to 1 minus A times tau.
Yeah.
Whenever we're evaluating the dynamics function, how does that end up working out or looking in an actual like equation?
Yeah, so the question is, in the dynamics equation that shows up here, just as one example, we have B times the sum of U plus W.
So it's not a function of.
So it's not a function. It's just a number. Yeah. B here, so suppose A is equal to 0.9, then B would be equal to 0.1 times tau.
But the big B that was derived from was a function.
The big B, like in the matrix derivations that we did, going from the continuous time to the discrete time form, big B there was a matrix and not a function. But it would just be a list of numbers in a matrix form. Yeah. Yeah. No, good questions. And yeah, this notation is a little bit fuzzy, right? This could also mean B is a function that eats U and W as inputs, but that's not the interpretation here. It's just a number. It could be 0.7 or something like that. And one wrinkle in the latent thermal storage model is that the self-dissipation time constant here is infinity in these models. So A, rather than being an e to the minus dt divided by tau, is just equal to 1. And then B, we get a simpler form as well. It's just equal to the time step. And these, in fact, are the limiting values of the A and the B that we get from the things that have finite time constants. They're the limits as we take that time constant to infinity. And I guess I have a short proof of that here. So, okay, what happens to A and to B as we take tau, which shows up in both of those expressions, as we take tau to infinity? Okay, well, this thing here, e to the minus delta t on tau, that is fairly easy. As tau goes to infinity, delta t on tau goes to 0. Anything raised to the 0 power is equal to 1. And so we get this limit as straightforward. The limit for B, however, has A, which has this exponential with a tau in it, and tau. So we have a product of two functions of tau. So we need to be a little bit more careful with understanding that limit. But it's not too hard. So we can define here alpha. This doesn't mean anything in particular. It's just 1 divided by the time constant tau. And then we want to find the limit of B here, 1 minus e to the minus delta t on tau, all of that times the time constant tau. So we can write that in terms of the alphas rather than in terms of tau. And then here we can use L'Hopital's rule. So this is something that you guys probably learned approximately 1,000,000 years ago in your calculus class when you were learning about limits. But if you have the ratio of two functions, the limit of the ratio is the same as the limit of the ratio of the derivatives of the functions. So here we take the derivative of the top and of the bottom. The bottom is very simple. The top is also pretty simple. And now we have a fairly easy limit here. And again, we get just delta t. So nothing too hard there, just kind of convincing you that there's a relationship between the sort of imperfect, the models that have self-dissipation and the model that has no self-dissipation. All right, and then the whole model, all the details basically look exactly the same as stratified sensible for the latent case. All right, so now we're going to go back and kind of take stock. We're going to look back at all the different models and say, okay, what can we write down that's sort of a general description of any of these sort of storage-like DERs? So all of the models have scalar, first order, only one state, dynamics. This is not the only way to write down an equation for a DER. We know that, like, for example, a 2R, 2C model of this room would have two states in it, and it would not directly reduce to a one-state model. We had to assume some time scale separation and things like that to basically decouple the mass dynamics from the air temperature dynamics. So anyway, this isn't perfect, but it's meant to be kind of a reasonably accurate description of a bunch of different DERs. And by the way, the reason that we're doing this is that, or one reason that I'm doing this, part of it is I just think it's kind of cool that like one set of equations can pretty much cover everything that we've talked about so far. But also as we begin to move into optimization, I will do some examples that have kind of generic DERs that are sort of modeled in this form. And so you can think of those examples. I'll probably talk about them in terms of batteries, because that's just like what's more concrete. But you can also think, oh, okay, but this battery model could represent air conditioning in a building, or it could represent an ice storage system for a big office building or a factory, something like that. Okay. Anyway, we have scalar, linear, time invariant dynamics. So time invariant just means that the parameters A and B don't change from one time step to the next, whereas the actions and the disturbance W here can. We have linear, time varying state constraints in general. So of course, if something is constant with respect to time, you can look at that as a special case of a time varying thing, just with a very dumb form of time variation, which is no variation at all. So some models we have constant x min and x max, and others we have time varying x min and x max. And then again, we have these kind of box constraints. We have a lower limit and an upper limit on a scalar action in each of these models. And then in general, to capture sort of all the behavior of all the different models, including the weird ones like the passive thermal mass one, we need a nonlinear equation to basically map the state, the energy stored, and the action, which is usually interpreted as like a charging power, to map those into the electric power P here. So we need, in general, nonlinear and time varying, although for many of our DERs, in fact, it ends up being linear and time invariant. Okay. So the parameters that show up in here, the A and the B, need to be defined in order to sort of instantiate this model and use it for simulating something, something real and interesting. We'd need to define A and B. We'd need to define W at every time step. And then we'd need to define the upper and lower limits for energy and power at every time step. And then as well, we'd need to define this function G. So we'll go through basically for each of the devices how we do that. The dynamics parameters are the same with this exact definition for basically all of the DERs except for the latent thermal energy storage model. And there we have the limits again of the A and B here as tau goes to infinity. So the limit, sort of the no self-dissipation limit gives us A is 1 and B is delta T. The disturbance, the W term there, is 0 for stationary batteries. It's 0 as well for the indoor air and shallow thermal mass and for the deep thermal mass model. But for the other models in general, it's not 0. So for electric vehicles, it's related to the energy dissipated for driving. And for the active thermal storage models, it's related to basically the energy that's withdrawn from the storage system, for example, to provide some process heat for an industrial facility, or to provide space conditioning for a building, or provide hot water for showers, something like that. The state constraints, so the x min and the x max, are time invariant, meaning they don't change with respect to time for batteries, both the stationary and the EV models, and also for the stratified and the latent thermal storage models. But for the sensible, the lumped sensible thermal storage model, if you look back, we find that we had actually time varying state constraints. And in general, we have time variation for the other passive thermal mass models as well. Okay. And then the U-min and the U-max, what we call the action constraints, those are time invariant for stationary batteries, but for everything else, they vary with time. So even for an EV, your charging and discharging limits are going to vary depending on whether you're plugged in or not. Yes.
You say stationary batteries, like what, like just something that would always be plugged in, that's the idea?
Yeah, so stationary battery, yes, it's just something that's always plugged in.
Just like a wall, Tesla battery.
Yeah, a great example of that would be a Tesla power wall, which would just hang in a garage. A chunk is bolted to the wall.
Okay.
It's always plugged into the building. Yeah. Mm-hmm. So stationary battery just means like not an EV battery. It's all sort of all other batteries, if that makes sense. Well, not exactly true. I guess a laptop battery, a
Right,
phone
yeah, exactly,
battery
yeah, that's
would be
what I
more
mean.
like an EV. They're plugged in, they're unplugged.
Yeah,
Yeah, yeah.
It's just ignoring like power out to some extent. So it's not technically plugged in anymore.
So like, what about a stationary battery in a power outage? Then in some sense, it's no longer plugged in. Um, it depends. So some people install batteries as backup, right? And so they deliberately wire them and have the controls set up so that when the grid goes down, they can still power the house or some of the devices in the house from the battery. So if you have the wiring and the controls, the power electronics, et cetera, to make that happen, then I would say yes, time invariant, even if you're subject to power outages, basically. But in other applications, you may have a stationary battery, but for example, you might not be allowed to discharge the battery back to the grid during a power outage. So there are similar rules around solar. So if you have solar, you may still have your solar shut down during a power outage in order to basically make sure that power lines are not hot when line workers go out to fix them during power outages. So yeah, there may be cases where actually you would want a time varying constraint related to whether or not there's a power outage. So yeah, that's fair and a nice point. Other comments on this stuff? Yes.
Just a reminder
Mhm.
from the thermal mass.
Mhm.
We assume that the air temperature doesn't have an effect on the temperature of the thermal mass. It's like it's time varying only because if like it gets cold outside in the winter, its thermal mass is lower than.
Okay, so the question is, why is for the deep thermal mass, why is that one? Why is the action constraint time varying?
Why is the state constraint?
Why is the state constraint time varying for the deep thermal mass? Okay, so let's go back to that one because I actually don't totally remember. Okay, so the state constraint here is time varying because, or so we'll get to the state constraint, is time varying here because why? Basically because this baseline T mass hat, which tells you sort of what the temperature of all the materials would be if we weren't messing around with it and doing something clever, right? That might potentially vary over time.
It's not because of any interaction between our actions. Like we had a trickle down effect with HVAC section where we change this, we preload, then it's got they're coupled in that way, but that's not the case.
It's not what's going on here. Yes, like so we had an example where if we change the sort of the nominal temperature set point, then we had this like weird jump behavior in one of the energy definitions. I guess that's not exactly what's happening here, although here this T min, the minimum allowable temperature for the thermal mass. Actually, this is maybe not the best definition because I'm not even sure how you would specify this. Like, what is the lowest thermal mass temperature that is unacceptable or uncomfortable for people? It's hard to know. Like, how cold can that wall get?
To geo, then that makes sense.
Yeah.
Because if you don't want whatever the temperature, if you push it past a certain temperature, you can't get back up.
Right. You think for like a geothermal system? Yeah.
No, like saying like what how cold you can let your chair get.
Yeah, it's hard to pin that down, right? But I guess you could imagine that varying with time as well, depending on like whether there are people in the building or not. Functionally, I think you could probably just like delete these constraints and just say, you can make the thermal mass as hot or as cold as you want. Because I think the temperature swings of the thermal mass are usually pretty small, but the energy storage capacity of all these materials is usually pretty high. So you get pretty big energy storage for pretty low temperature swings. That makes sense. Okay. All right. So that was, we went through the action and the state constraints, and then the output equation here. I guess, takes its most general form. Well, not quite. It takes the nonlinear form, but it is time invariant, meaning the function that maps the stored energy and the charging or discharging power into the electrical power. That function does not depend on time for the both of the battery cases. But it's nonlinear there because we had essentially the imperfect charging and discharging efficiency. So we had that kind of piecewise linear kinked plot. And then for everything else, the output equation is linear, but it is time varying as well, and independent of x, the state, except for the deep thermal mass, where it's really weird. But we have a linear and time varying output equation that also depends on the state. So this is why we put in that function g, we put in the dependence on x, basically to accommodate the deep thermal mass model. And we put the dependence on time, k, in order to accommodate these time varying models. All right. So that is all the math for, well, I won't promise that, but most of the math for today. And so now we're just going to talk about a few other DERs, just briefly in passing. Each of these is interesting in its own right and can be a valuable DER. So maybe in your project, you'll want to think about one of these. The reason I haven't talked about them explicitly is because either the modeling is fairly simple, they're not used very often in practice for DER stuff, or they can be modeled in a way that is quite similar to something else that we have already modeled. So one of these categories is refrigerators and freezers. So here, I guess this is a fridge on top, freezer on the bottom, something like that. There are about 125 million homes in the US, and some of those housing units have multiple refrigerators or freezers. So there's about 200 million of them total in the US. And each of them has some flexibility. In the same way we talk about playing these games with adjusting temperatures inside of a building, you could imagine playing similar games adjusting the temperature inside of a fridge. So you could pre-cool some food or deep freeze some food, something like that. And then during a period when the grid is stressed or electricity is really expensive, you can imagine basically locking out or not using the cooling system. So a typical freezer or fridge might use sort of on the order of 0.5 kilowatt. If you take that and you multiply it by the 200 million fridges and freezers that there are in the US, you get about 100 gigawatts of potentially flexible capacity, power capacity. And just for comparison, that's about 1/13 of the total electricity generation capacity in the country. So not a small amount of flexible capacity. If you imagine you got all the big manufacturers together and you said, hey, we want to use a little bit of that flexibility to be able to wiggle around what fridges are doing, you could imagine providing a very significant amount of grid services from that. And a cool thing about a fridge or freezer, and actually we had a project team that kind of thought about fridges and freezers last year in this class, but you can model them essentially in the same way that you model a building. So you could use either a 1R 1C model or maybe a 2R 2C model where you'd have different temperatures, for example, for the air in the fridge and then the food in the fridge, or you might have a freezer temperature and a fridge temperature, something like that. But you can kind of think through how you would model one of these. Another category here would be, so I would call these something like a storage-like load. They basically, you could do all the same games that we did with the passive and the active thermal mass, those battery models, and we could put these into the same framework that we already are working with. Yes.
Isn't this one like inherently different between the buildings though, because we care about what the temperature of the thermal mass is? Like, so you can't just like pre-cool and freeze the crowd out of there.
Yeah. It's a good point. Yeah. So we were just saying how like who really cares what the temperature of a wall is? But if you're dealing, say, with the fridge compartment here, we might really care what the temperature is in there. If we make it too cold, we could freeze stuff. You could smash your beer bottles or whatever it is. And even in the freezer, there's usually temperature range that stuff likes to be kept at. And if you go too deep, it can cause changes in the food and stuff. So yes, it is different. And I think you would have kind of constraints on that that would filter into an optimization model or something like that. Yeah.
So the fridge is used exclusively to hold pizza.
Yeah, exactly.
How many pizza are there?
Yeah, right, right. So if you only had pizza, you could imagine coming up with the temperature limits. But if you had a bunch of diverse types of food, you might have different. I guess you use the tightest limits, whatever the most fussy food is. I guess you don't want to freeze your lettuce or something.
Live. See,
Live seafood. Yeah,
keep it moist.
right, right. Okay, so something that's not really a storage like load, something that I don't think could be put, at least not as easily, into the sort of battery framework that we talked about, would be what are called deferrable loads. So you can think of things, some things like appliances that just need to run before a deadline. So a classic example of that would be a dishwasher. You load up the dishwasher at night, you put some soap in, you don't really care if it runs immediately or if it runs from 4 to 6 in the morning. You just want to make sure that your dishes are clean for breakfast or something like that. Yeah, okay. So we might load at 8, we might need to finish by 6. It might take a couple of hours to run. And while it's running, it might use a couple kW on average. All right. So there's about 80 million dishwashers in the US. So not all housing units have a dishwasher, of course. And call it a kilowatt and a half each when they're running. That again gives you on the order of 100 gigawatts. So about 1/13 of all electricity generation capacity in the US. You get just from these flexible appliances. Yes.
This one, like, another real life example, company that I worked at, they worked with an airport and they did like peak shedding and that kind of stuff.
Mhm.
And just the time, just varying when each of the escalators was booted on and off, saved the company like hundreds of thousands of dollars, or saved the airport hundreds of thousands of dollars, because whenever they boot on, they use way more power than whenever they're just running.
I'm just going to repeat that for folks online. So Grant worked for a company that consulted with an airport. The airport wanted to save money on utility bills, and the company recommended basically staggering the times when the escalators boot up in the morning, I guess, before flights start. Because when you go through that initial boot up phase, getting all that, overcoming all the friction and the inertia and stuff takes a bunch of energy, I guess. And then once they're kind of in steady state, it's much lower. So they must have been all synchronized at 6 a.m. or something like that, leading to a huge peak in power consumption in the morning. And they probably had a peak demand charge that was killing them for that. Okay, cool. That's a cool example.
Just quick question, how would you, like, let's say you could get everybody in the US who had a dishwasher, one that would, like, you could program to run at a certain time.
Yeah.
You know, assuming you can overcome that barrier, you know, like assuming all dishwashers are smart dishwashers, then would you tell people, and like, okay, if you live in this county, run your dishwasher from this time to this time, or like, how would you manage it such that you would say, okay, we can actually create, you know, a sustainable or, you know, low demand that is, you know, fixed or, you know, steady throughout the course of the night, rather than everybody being like, oh, 3 a.m. sounds good, and then at 3 a.m. there's like a peak just because, you know, everybody had their dishwasher set to that. Yeah.
A cascade. You guys get
Yeah,
it?
that's good.
The dishwasher.
That was. All right, so to paraphrase this for folks online, what if wave a magic wand? Wait, I missed something. I'm sorry. Suppose you could wave a magic wand and all the 80 million dishwashers magically became
Well,
smart
yes, that-
and internet
that's what you
connected.
need to do to get this flexible capacity, right?
Yeah.
Because, yeah, like you're set up in a scenario where you can take advantage of flexible capacity. Because, like, I mean, I have a dishwasher that's like compressed and it starts, and I'm not going to get up at 3 in the morning to go press
No.
the dishwasher. You know?
Yeah, so you need the smarts built into them. So suppose they all have this, and some of
Yeah.
them do, but most of them don't. But imagine you're in a future where they all did.
Yeah.
And the question more or less is like, what would you do with
Yeah,
that
how
if you
do
had
you-
it? Yeah.
Like, who would be with the power company say, hey, you guys should run your appliances at this time to save the most money, or would they set that up, or would it be like, how would you go about that?
One might say that you'd have two controllers, one that works for the utility and one that works for the house, and the house would like monitor the demand of the house. So it's trying to optimize like,
Yeah.
the peaks there,
Mhm.
and then that one communicates with the utility one.
Hmm.
And then they communicate with all the different houses. So they don't care if you've got a smart washer or a smart dryer or you know TV that's really, really bright. They just want to monitor the total load.
Partially comes down to the article you gave at the beginning of the semester, where should we have some governing body that controls all smart devices, or all smart devices are controlled at some level to tell people above, hey, I want 1.5 kilowatts.
These are really good questions and good discussion. I'm realizing maybe I should give you guys a little bit more reading material, and maybe we can do like a read and discuss sort of class about some of these ideas. There was some back and forth just for the video about who basically controls that. Is it the utility that basically decides from the top down what happens? Do the devices decide from the bottom up? Is there some intermediate intelligence? Do different autonomous systems talk to one another and kind of find a compromise?
Like within a house or something like that, yeah. I would feel a
Yeah.
little bit uneasy about I think I'd be okay with it, but if my dishwasher were like, hey, I'm running from 4 AM to 6 AM, be like, okay, like good for you. But
Yeah.
I would be a little concerned if like somebody in, Chicago were like, okay, your dishwasher's gonna run at 3 AM tonight. Not that I'd be against it, but I'd be like, well, you can do that? Like, that's so
Yeah.
scary.
It's a little weird. There are privacy, there are cybersecurity type concerns as well. Yeah. So just so you guys know, this is an active research area and an active area of product development. And there was a big push at the Department of Energy under Biden. Who knows if it will continue under Trump, but to basically kickstart researchers and industry to sort of answering all these questions and moving forward to scale up what are called virtual power plants. But the basic idea is that you have millions or tens of millions of devices. How do you coordinate their operation to do good stuff for the grid, right? So I think the next reading that I'll give you guys, and maybe we can do a discussion class and maybe after spring break or something like that, but we can talk through some of these ideas and pros and cons and stuff. Cool. Okay, I'm just gonna move forward here. Oh yeah, washers and dryers are another example of deferrable loads. But again, this stuff is all sort of residential focused, but all of these ideas work in the commercial buildings area. So when you start talking about offices or hospitals or educational facilities, and airports are another great example with escalators, saving an airport hundreds of thousands of dollars by staggering the operation, the boot up of the escalators. And they work in industrial settings as well. So, you can think of something like an aluminum smelter that needs to, basically, I don't know, smelt a bunch of aluminum. And it doesn't necessarily have to happen at exactly noon. It can be sort of spread out over the course of a day. And so a huge piece of equipment that uses enormous amounts of electricity like that, there might be a lot of value in shifting around when exactly that thing runs.
My parents work for NASA. They can only test at night because of how much power they draw from the grid. So we'll deal with stuff of we'll pull from 1 AM to 6 AM and then we'll cut.
So you
can't do both.
Yeah.
Like city and NASA.
So your parents work at NASA and they have some stuff, unspecified stuff, or can you tell us? Wind tunnels, just normal flying saucer kind of things. Yeah. Oh,
Structures,
sure.
Stuff. So like the fan itself is 24 feet.
Okay.
It takes power, and then like all the cooling. Like my mom does a lot of clouds. She makes clouds for a living. And so
cool.
It takes a lot of energy to like cool the water all the way down to super cool droplets and then push the air fast enough. The other thing.
So they have lots of testing apparatus, huge fans, huge cooling coils and stuff like that take a ton of power. And the local utility basically can either power their testing facilities or can power the nearby city, and not both. And so they only can test at night basically for that reason. Yeah. Yeah, and right, exactly. So that's an idea, an example of a deferrable load. You need to do a certain amount of testing this month to deliver on your grant or your project or whatever it is, but you don't exactly care whether it happens at 2 AM or 4 AM, something like that. Yeah. Okay, some people in their project pitches last week talked about wind. I thought about doing a whole lecture on wind, but then I was like, well, is wind really a DER? Most wind turbines that are built today are like really big, and they're built in big farms that are more kind of like, traditional central generation capacity. But there's also small wind turbines, and I think one group wants to work on what's called a vertical axis wind turbine. So rather than like a big fan looking thing that spins like this, something that spins on a horizontal axis. So anyway, talk very briefly about modeling wind and some of the considerations that come up there. Okay, so the power output, call it P, from a wind turbine basically scales like the cube of wind speed. And this is actually similar. We talked about pump and fan affinity laws. So where the power consumption of a pump or a fan goes kind of like the cube of the speed of whatever fluid it's pushing. It's basically the same math and the same physics, but just run in reverse for a wind turbine. And then just because physics again, wind speed, call it V, typically scales like the height of the sensor of the wind speed, but in this case, the height of the turbine, raised to the power of about 0.2. And this coefficient here, I forget what it's called, but it varies depending on elevation and location and temperature and stuff like that. But this is kind of a typical value. Okay, so then I'm just writing down these equations. Here's the cubic dependence on wind speed of power, where P naught and V naught are the power and the wind speed at kind of rated conditions. And then wind speed varies like y, so the height to the power alpha. And so if we put these equations together, we get that the power varies like height to the power 3 alpha, or about 0.6. And here's what that dependence looks like. So here we have the ratio y divided by the rated height, or sort of the height at which maybe the measurement of wind speed is happening. And then on the y-axis, we have P divided by P naught. So you can see it's kind of a nonlinear dependence, and it's got a coefficient less than 1. So if we drew the line y equals x, it would look kind of like this. But the basic trend is that we get more power out, basically, if we make a turbine taller. For various reasons, but one is the scaling of wind speed with elevation. And so for reasons related to economies of scale, typically that means that the taller you can get with a wind turbine, the more cost effective it is in terms of generation. And this is why over the last 10 or 15 years, we've seen a trend toward bigger and bigger and bigger wind turbines. And so I think that this is currently accurate. I have this slide, I put it up every year, and I need to kind of update it every year because the world record for biggest wind turbine in operation keeps getting bigger and bigger each year. But this is one turbine that I think as of late 2023, early 24, was the biggest in the world. It's an offshore wind installation. You can see this is like a gigantic freighter ship, right? And then, so this thing, the blades, so the radius of the cross-sectional circle here that this thing sweeps out is 130 meters. And for comparison, a Boeing 747 is about half that. It's about 70 meters long. So take the biggest plane that you've ever been on in your life, put 2 of them nose to tail, and they're about the length of one of these blades. Anyway, so a simple way to simulate wind power, if you need this for your class project, typically we get from weather data, you can get wind speed information and wind direction information. By the way, most horizontal axis wind turbines have like a pivot in them where they swivel so that they're pretty much orthogonal to the wind, so they get the most energy out of the wind that they can. Okay, so you get the wind speed at some height that you find from the weather data, maybe 1 meter or 10 meters, whatever is reported. And then we use this kind of scaling law here, approximate scaling law, to back out what the wind speed is at the actual height of the hub of the turbine. And then you look up the type of turbine that you're modeling, which typically would have what's called a cutout and a cut-in speed. So these are big rotating machines. They don't like to operate at very, very low RPM or at very, very high RPM. So basically to protect the bearings and the components of the machine, they will turn off when there's very low wind speed, and they will also turn off when there's very high wind speed. So I live kind of near downtown Lafayette, where you can look out and see a couple of wind turbines that are off in a park down there somewhere. And you'll see sometimes even on a windy day, the turbines aren't spinning at all. It's sort of confusing, but sometimes that means that there's too much wind for them to safely absorb. Okay, so then if you're between the cut-in and the cut-out speed, then basically we use our cube law again to scale up the power consumption from the rated velocity. And sort of actually more likely we would scale this down from the rated velocity. And we know the rated power might be 15 megawatts for a really big turbine, to scale that down to the actual power output. And then if we are either above or below this range, sort of the safe operating range, then we just set the power equal to 0. Yes.
On those particularly windy days, could the wind turbine just turn so that it's more parallel to the wind, or would that, I assume, maybe mess something up? I don't know, but just like increase like the magnitude at what, how much it's spinning.
Yeah, so the question is, could you sort of say the wind is coming directly in my face and or I'm above the cutout speed, could we angle the turbine sort of a
Yeah.
bit to basically reduce the amount of kinetic energy that it would suck out of that air? I think you probably could, and I think they probably don't, because I'm not totally sure about this, but you might get weird stresses and stuff on the turbine blades that might lead to more wear and tear than it's worth in those conditions. But I'm not sure. It's an interesting question. Okay, I'm just going to go through these last 2 slides very quickly since we are at time. Right, so some things burn fuel. So this could be backup heaters, it could be furnaces and things like that. Diesel generators, another example of a DER that some people will use. For example, turn on a generator in the basement to reduce power at peak times. And there's what's called combined heat and power, which is also known either as cogeneration, if you provide, say, steam for space heating and also electricity, or trigeneration, which is what the Purdue utility plant does. So they produce chilled water, very cold water that's used for space cooling. They produce steam that's used for space heating, and they produce electricity. And then there are ways to use fuel to basically get the energy that's stored in the chemical bonds in the fuel without burning it. So by undergoing other reactions, so not combustion reactions. So a natural gas or a methane fuel cell is one example there. Hydrogen fuel cells are another example. And there are various uses for things that use fuel. They can be used for backup, either backup heat, backup power. They can be used to stabilize a microgrid. So you could imagine building a solar microgrid that to run autonomously only off of solar, you might need an enormous battery. But if you had a little bit of natural gas generation, for example, you might be able to get away with a much smaller battery and a much smaller solar array. And then most of these things, I think the simple way to model them is just to get an efficiency estimate and model the output, whether it's the power or the heat that it's producing, as the efficiency times the input. And this equation, very simple to implement, and it usually gets you, not all the way to an accurate model, but 80, 90% of the way there. And this is just a quick sketch of what a combined heat and power system looks like. This more or less is what the Purdue power plant does, although it also produces chilled water. But the idea here for folks who have done thermodynamics recently is you would have an air cycle, a Brayton cycle, that takes in air, compresses it, runs it through a combustion chamber, expands it in a turbine to produce a work output. And then you would take that still pretty hot, pretty high pressure air that comes out of the turbine and run it through a heat exchanger to boil water in a Rankine cycle. That boiled water would flow through a turbine, again, expanding there and producing a work output. And then it would flow through a condenser, basically to cool down and condense that, say, water that's flowing through the turbine. It gets pumped back around the cycle. And then the heat rejected in that condenser by the working fluid gets picked up by a steam loop, typically. So you boil some water here and make steam and then ship that around to, for example, heat buildings or heat labs and things like that. And this is, it can be very, very efficient. So combining just the power generation, having 2 cycles, you might get an efficiency of sort of 50 to 55% range, assuming you're using good and modern equipment. But then if you also extract energy to use for space heating, the overall efficiency might be, in the 75, 80% sort of range. So it's pretty much the best that you can do in a fossil fueled setup. Okay, that is all for today. Any questions? Okay, so just as a reminder, no in-person class on Thursday. We will have class on Zoom only, and it'll just be Q&A. So if there's stuff that you're stuck on for homework or whatever, bring some questions on Thursday.